Welcome back to the introduction of MEMS series. Today we're going to talk about MEMS process integration, which is to put design, materials, and processing together. My name is Chang. A good MEMS practitioner needs to know three things: the design, the fabrication process, and materials. Design, for example, mechanics and physics, fabrication processes, and materials. So the elements are intertwined. If you have a good design, then it may also need a good material, and you also need a good fabrication process. The goals might include, for example, better performance for the machinery, better yield, uh, some unique advantages of the device that you're making, and lowering the cost of the overall device so you have a chance of making profits. A good MEMS person needs to know all three things and understand the relationship between this. The selectivity of etching is very crucial. There are papers published in the past that summarizes etch rate for micromachining processes. That's basically a huge table of different etchants on different materials. And this is something that every MEMS engineer should know by heart, especially the ones with good selectivity. For example, hydrofluoric acid does not etch silicon nitride, but etches oxide very selectively. Things like that. This kind of table is helpful. However, you need to realize that this is not like a Bible, right? Because every lab is different. Every concoction of chemicals and materials are slightly different. Every machine is different, and every run may be different. And this is something that accounts for the variability of processing. A good designer uh, of process and machinery needs to consider the variability. The criteria for selecting materials and etching solutions are the following. Number one is selectivity. The etch rate on structural layers and the etch rate on sacrificial layer must be as high as possible. You don't want something that is below 10, for example. In that case, you have to do extremely good timing control. And timing control is always not good for production because it's not robust. The etch rate needs to be considered. Ideally, we want high etch rate on sacrificial layers to reduce etch time. The temperature of the material is important, especially the deposition. In certain applications, it is required that the overall processing temperature be low. For example, the integration with CMOS. CMOS cannot take too much high temperature, and the bumps and solders may melt. So all these things needs to be considered. The intrinsic stress of the structural layer needs to be considered. Some materials have stress, and this stress is intrinsic upon the completion of its processing. So if you want a structure to remain flat, then you need to identify materials where the intrinsic stress is zero or can be controlled. Surface smoothness is obviously important, and long-term stability is important. If you have a material whose property changes after a few runs, then you don't have a product. If you don't have a product, then you have no prayer of making any money. People need to be able to choose hybrid processing where bulk micromachining, surface micromachining, three-dimensional assembly, and wafer bonding are all mixed together for the interest of a best product. And a good MEMS designer should be able to understand all these different categories of processing capabilities. The typical structural and sacrificial compatibility is something that every MEMS engineer needs to know. And some of the most common sacrificial layers are oxide, photoresist, parylene, and metal. And if you use them as a structural layer, polysilicon, silicon nitride, metal, photoresist, and parylene, then you can look at which one give you a okay combination. I'm not going to discuss all the details, but you can read it. And if you have any questions about this table, please feel free to submit your questions in the comment section. I'll answer them personally. The compatibility table is very crucial. You not only want to have uh, the table from a standard textbook, but sometimes you need to build one for your own. Let's talk about some of the processing uh, complexities. Uh, in terms of uh, making up a process, you can have a simple one, like the one we discussed before, where you make a surface micromachine rotor using two structural layers, and two sacrificial layers. In this case, the sacrificial layer is the silicon dioxide, and the structural layer is the silicon nitride. Now you can make it more complex. For example, you can add a dimple at the bottom of the rotor so the rotor does not get stuck to the substrate very easily. And one of the ways you can do it is to um, actually add a sacrificial layer, but partially etch away the material instead of completely etching. So this is an interesting feature, but it requires timing control of the uh, of the etching process. Once you have a sacrificial layer with a dimple, then you can continue with the first layer of structural layers, second sacrificial layer, and the next structural layer serving as anchor, and so on. This process, compared to the previous one, obviously would take more time. The cycle time would be longer, the robustness would be lower, and but it does result in a better, more robust process, uh, and perhaps a better rotor. This is the third and yet most complex rotor structure. It consists of bushing with silicon nitride anti-friction ring. Let me explain how this is done. You have a silicon oxide and you grow a silicon nitride layer, and this nitride layer serves as a underpinning. You deposit a first sacrificial, uh, you deposit a polysilicon layer. Uh, it's red, and this is the first sacrificial layer material. This is then patterned and then coated again with the second polysilicon structure. The polysilicon is patterned and then covered conformally with a silicon nitride layer. Now, the silicon nitride layer can be patterned and etched using plasma etching. If you control your plasma etching process well, it will become anisotropic, namely the surfaces that are facing the electrode would receive more faster etch than the silicon nitride on the edges. So this way you can leave some silicon nitride on the vertical surfaces, but remove all the silicon nitride on the frontal surfaces. And after this, you can do a timed uh, isotropic etching to create desired undercut. The undercut creates a spacing. After this, you can deposit yet another sacrificial layer and then coat it with another silicon nitride material. The silicon nitride material, as you can see, will reach underneath the first polysilicon layer, uh, would reach underneath the rotor material and form a shelf that can support the rotor from falling to the substrate. After you remove all this sacri- uh, After you remove all the sacrificial layer, then you have a very delicate structure with uh, features that prevent the rotor from falling to the substrate and getting stuck. And you have silicon nitride bushing that reduces the friction. This obviously takes the most time and is the most advanced technology. Now we know that a MEMS engineer needs to consider design, fabrication, and materials. Let's look at a few case studies. Case number one is an electrostatic actuator. So this is a beam that you can control its tilt using electrostatic force. The process goes like this. You have a intrinsic silicon substrate and a oxide mask is placed on top. Is patterned and the oxide is etched to expose the silicon. In this silicon region, you can dope the uh, surface silicon region to have a higher concentration of conductivity change. Then we grow a layer of epitaxy silicon. This is single crystal silicon. The oxide is then grown on top of this epitaxy silicon again and patterned. Part of the oxide forms a opening window that allows anisotropic etching to happen to open up the underlying high conductance region. The other two windows on oxide is used to dope uh, with a source and drain so that you can integrate electronics with some MEMS monolithically. You grow a layer of gate oxide and use the common process to grow MOS transistors. After this, we use a silicon uh, gas phase silicon etch or liquid phase silicon etch to remove the sacrificial layer. In this case, the sacrificial layer is the silicon itself. The beam consists of a metallic layer and a silicon layer. So what's one of the advantages for this is that the beam would have an intrinsic stress that bend up. This prevents a flat beam from being uh, sucked to the substrate during release. So what's the pros and cons of this? Right, the design aspect. The the good thing is that this allows the mechanical cantilever to be directly integrated with field effect transistors. So you could have low noise sensor because the electronics and the sensors and actuators are together. In terms of materials, it's relatively exotic, and the wafers are also exotic because you need to grow epitaxy silicon and then later remove it. The process difficulty mainly is the uh, cantilever release using wet silicon etchants. This was not something that's done very common. Now, second case is a torsional capacitor accelerometer. This device consists of a imbalanced uh, proof mass. So the proof mass is heavier on one side and light on the other is connected to a torsion beam. If you have acceleration, then the uh, spacing would change and the capacitance would change. Now, this can be done with a surface micromachining process. We start with a silicon wafer. You go through the routine oxide growth, patterning oxide to dope selective regions to have high conductivity. Then we grow a layer of oxide. Um, we grow a layer of metal to cover the front surface. Then we grow another layer of metal too as the sacrificial layer. The metal is patterned with a via, and this is used then to electroplate nickel. The reason we have to use metal as a sacrificial layer is so that we can have a seed layer to do electroplating. Now, why do we have to do electroplating? Because in this case, it is one of the easier ways to grow thicker plate and heavier mass, so we can increase the sensitivity. Now, what do you think about this? Leave your comment below about pros and cons in terms of designs, materials, and fabrication process. Now, the last example we're going to show is a membrane parallel plate pressure sensor. This is a fancy pressure sensor, and it consists of a silicon shell with a capacitance. Now, how do we make this device? We start with silicon wafer, grow oxide as a mask window, then etch this to form a cavity of desired depths. The oxide is removed and then regrown again so that oxide covers both the top and bottom of the cavity. We use photolithography to pattern the oxide. Now keep in mind that the oxide or resist spin coating on the bottom of the cavity is not going to be easy, and the focal depths on top and in the bottom of the cavity are not the same. Using the oxide, we use it as a doping window. So we heavily dope the regions that are exposed directly. And after that, we have the sculpted region as doped profile. The reason for this is because doped silicon have a much lower etch rate in silicon etchant. Then we grow a very thin layer of doping to form a shell, complete the sculpted shell. After this, we grow the insulator material. This can be a dielectric material such as PECVD oxide. Then we grow a layer of conductive polysilicon and then chrome gold oxide as a conductance. The chrome gold is here used for bonding. This is bonded to another silicon wafer with a metal on top. And after this, we can use a dicing saw to cut this die and use the silicon etchant to selectively remove the silicon on top without touching the metal and without touching the conductive polysilicon. This is a very interesting and rather delicate process. So what do you think about this? Comment below. These are not examples of commercial high volume products, but nonetheless, they are, I hope that they provide some mental exercises for people who are interested in evaluating the pros and cons of MEMS designs, fabrication, and materials. This is the job of an integrator. Thank you. Now here's a pop quiz. Um, which process below are better for forming a membrane? Number one process forms a silicon nitride membrane, LPCVD silicon nitride. Number two process forms a silicon membrane. So in terms of materials, single crystal silicon is definitely better than LPCVD silicon nitride. However, this process is very sensitive to timed etch because the cavity depth is completely controlled by the timing, by amount of time. Whereas this one, the silicon nitride thickness is predefined by LPCVD deposition, which is a lot easier to control. And in terms of design, um, if you want to put a piezo resistors on top of this, you have to deposit another layer of poly. Whereas in this device, if you want to put piezo resistor, you might be able to just dope it, and it would have a higher piezo resistance sensitivity. So there you go. You have different pros and cons. Very rarely you have one material system, one design, one fabrication process that's favorable in every aspect. So the rules for surface micromachining is to have high yield process. The only process that's acceptable is a high yield process. High yield process meaning the process itself is robust, it's not sensitive to time, it's not sensitive to a lot of parameters. These are the rules for surface micromachining. Materials on top should not hurt any material on the wafer already. When we pattern the structural layer, we shouldn't affect any of the materials already on there. And the sacrificial etch process should not hurt any other material. If you can satisfy robustness in all three aspects, then you have a really, really good process. And you have aced the MEMS integration game.